So an action of a group G on a set X is a map from G times X to X, which satisfies two very simple axioms. First, the identity element of the group acts trivially, and secondly, the product acts by composition. So if I take the product A times B in the group applied to X, then I get A times B times X. So that's very simple, but somehow one of the main thing that one does using groups is study group operations. One also studies them to understand groups. So one example that we had and that plays a role also in what comes is the very simple one, the left multiplication. So that is L from G times G to G, sending just the product in the group. And we had used this to prove Cayley's theorem, which said that, for instance, every finite group is a subgroup of a symmetric group, is isomorphic so the group is called G to a subgroup of the symmetric group in as many elements as the elements in G. Okay, so that's maybe as much as I wanted to say as a review. Then now, two important notions that we have about group actions are the orbit and the stabilizer. The orbit of an element in X is just all elements in X we can reach by acting by an element in G. And the stabilizer of an element X are all the elements in G that don't move X. So definition. That again, G act on X. So the orbit of X in X is usually denoted Gx, G of X is just a set of all G times X with G and G. This is a subset of X, obviously. And such an, a subset of this form is called an orbit of G on X. So clearly we had introduced transitivity for action. Clearly an action is transitive if there is an X in X such that its orbit is the whole of X. So we can also say that the group action, so the action of G on X defines an equivalence relation whose equivalence classes are the orbits. Namely, you can say that X is equivalent to Y if and only if there exists an element in the group which sends x to y. This is clearly an equivalence relation, and clearly the equivalence classes are the orbits. Okay. So then another notion. So in particular, it follows. I mean, that's also anyway clear that it follows that X is a disjoint union of the orbits of G on X. No, two orbits are either equal or disjoint, and their union obviously is the whole of X. So another notion is the stabilizer. As I said, it's all elements in the group which don't move X. So the stabilizer of X in X is, so I often usually denote it just Gx. It's a little bit similar to the orbit, but still, if one wants to say precisely where one is, one can also say stub X, but I usually write Gx, which is just, as I said, the set of all elements in the group which do not move X. So this is clearly a subgroup. Of G, as follows. You can see directly, no, there's no, it's obviously a subgroup. And we have some, we can see some, we have this very simple lemma, which is more a triviality, which is that the orbit Gx, G of X, is in bijection to the cosets of G modulo Gx. So there's a bijection, so let X and X. There is a bijection. So from G modulo cosets modulo the stabilizer to the orbit of X, sending, say, the coset of an element G to just G times X. So the obvious thing. So in particular, if, say, the orbit is finite, the number of elements in the orbit is equal to the index of Gx in G. While also in general is finite, we have that number of elements in the orbit of X is equal to the index of Gx in G. Okay, that's clear. And this statement takes longer to state than to prove because there's an obvious, here is the map, we just have to see basically that it's well defined and then also injective. So this map, so G times Gx maps to X, is well defined at injective. So we have to see that two such things are mapped to the same thing if and only if and only if the G lie in the same coset. So let's see. So G prime Gx is equal to G Gx if and only if So if I multiply by g to the minus 1 on this other side, so if this times gx is equal to gx, so that means that this is an element in gx. And so that means this is an element in the stabilizer, so it sends x to x, so if and only if. Minus 1 g prime of x, so x. So, and then we can, then it follows that prime x of x. So if we apply here with g, if we apply the action of g on it and use the associativity property of the action, then it is this. And so we see that these two elements here, g and g and g prime and g define the same coset if and only if here we also have the same. And so this means this map is both well-defined and injective. And it's surjective by definition. Because in the definition here, this g is an arbitrary element of g, so therefore gx is an arbitrary element in the orbit. Okay, so this was this very trivial lemma, but basically this gives us the proof of the theorem, which is again a very simple theorem. It's very easy, but I call it a theorem because it's very useful and we will use it many times. So this is the orbit stabilizer theorem. So let's say, so let a group G act on a finite set X. So we take a set of representatives for the orbits, so a set which contains one element from every orbit. Then we can write the number of elements in X can be written as the sum over all X in R over the number of elements in the orbit, which is the same as the sum over all, X in R of the index of Gx in G. Okay. And so this is actually completely obvious. We have whatever there might be to prove, we just proved in the lemma. Clearly, X is the union of the orbits, so therefore the number of elements of X is equal to the sum of the elements in the orbit. So X is equal to sum because X is the union of the orbits. And we have just seen that the number of elements in Gx is this index. So, and by the lemma, we have that the number of elements in the orbit is equal to the index of Gx in G. Okay, so this was this orbit stabilizer theorem. So it's just a triviality, but it is a very nice triviality, that one that is very useful. So now we want to look a little bit at one particular action of the group G on itself, which is the action by conjugation. So, yeah. So, I don't know whether I already had introduced it as an example or not. Anyway, definition, the conjugation action of G on itself is defined by just we send, so G times H is defined to be G, H, G to the minus 1. It's straightforward to see that this is an action, an operation. And the orbits of this action are called the conjugacy classes. Of G. And we denote them, denote it for G. Okay, so this is the conjugation action. So I should maybe mention that this is somehow a very important invariant of a group to know what the conjugacy classes are, how many conjugacy classes there are, and so on. In particular, one very important tool to study groups or also use groups to do other things is the field of representation theory, where one studies homomorphisms from groups to the general linear group, GLN, R or C, and say GLN C, and then, so over the complex numbers, then one finds there's, for instance, these representations come in some kind of pieces out of which you can make all of them, and for a finite group, for instance, so these pieces would be called irreducible representations, and for a finite group you have a bijection between the irreducible representation and the conjugacy classes. So in some sense you understand all representations in terms of something which is associated to the conjugacy classes. So we are not going to study this, but I just want to mention it. Sometimes, I don't know whether he does it this year, but sometimes my colleague Villegas gives a course on representation theory, so maybe you will see things there. So now we want to look instead at things like stabilizer and so on for this action. So, so we have again G with the action by conjugation. So you can look, for instance, at the stabilizer of an element under conjugation. So definition, the centralizer say Cx of X in G is just a set of all elements in the group which commute with our X. So this is all G in G, such that Gx is equal to Xg. And note this is also clearly Gx is also equal to the stabilizer of X under the conjugation action. Because that Gx is equal to Xg is the same as Gx, G to the minus 1 is equal to X. But anyway, by itself, it's just a set of all elements which commute with our given element X. So by definition, so anyway, it's this stabilizer is always a subgroup. So this is a subgroup, which anyway also follows from the definition. And we can see by definition, we have that Zx is a subgroup of G, and the center of G, which is the set of elements, of all elements of G which commute with all other elements, so set of all G such that GH is equal to HG for all H in G, is a subgroup of Cx. Because clearly if something commutes with every element, it will commute with our given X. What? Ah. Yeah, okay, you could also say that Z of G is the intersection of all centralizers. I don't know whether this is useful sometimes, maybe it is, but anyway, that is certainly true. So, and we can also say, by definition, clearly, we have that X is an element in the center of G if and only if its centralizer is the whole of G. Because it just means it commutes with every element. So now we want to basically, we just want to apply this orbit stabilizer theorem to this action, and we get another result, which is called the class equation, which tells us, in some sense, yeah, how many conjugacy classes there are, or whatever. So let's see. So this is the following theorem. Basically just a reformulation for this situation of the orbit stabilizer theorem. So this is the class equation. So let G be a finite group. And that R be a set which contains one element out of every conjugacy class. Bigger ones. Element, one element of every conjugacy class. So a system of representatives for the conjugacy classes. Well, yeah, no, but I didn't want to say that because for some reason it's always stated in another way. So I write it differently, such that every element of G, not in the center, is conjugated to precisely one element of R. So we have a system of all conjugacy classes, a system of representatives of all conjugacy classes, except for those of elements who are in the center. And so then we have this very unsurprising fact that the number of elements in G is equal to the sum over all x in R. No, I see this. So first, the number of elements in the center plus the sum over all x in R of the index of the centralizer of x in G. Okay. So this, if you think of it, is also very easy or basically obvious. It's just a reformulation of the above. Namely, this is just the orbit stabilizer theorem when we remember that the orbit under the conjugation action of an element in the center is just that element itself, contains just one element. So let me just write it down. So proof. So let R prime be a system of representatives of the conjugacy classes of G. And then we have that G is equal to the sum over all x in R prime of the index of G of the stabilizer with respect to the conjugacy action of G, which is saying because the stabilizer is just Gx. And now we just note that if our x lies in the center, then its conjugacy class consists precisely of one element. Then just x. And so we can rewrite this as, so the above sum is x equal to the sum over all x in the center of G1 plus the sum over all x in R of the centralizer of x in G. And that is the statement. Okay, so this is also very simple. Now we want to apply this to study groups where the number of elements of the group is p squared, where p is a prime. We want to show that every group with p squared elements for p a prime is abelian. Okay. We'll use the class equation for that, and it's so first I define a P group, and we will need that later for zero theorems. So let P be a prime number. The P group is a group of order for some m bigger than 0. Or at least that's how I want to do it here. So we know that a group of order P is cyclic. And now we want to show that the group of order p squared is abelian. So first, we want to say that, as a lemma, we want to show that the center of a p group is always non-trivial. In fact, it has at least p elements. Center of a p group has order at least p. Okay, so let's see. It's actually also quite simple. That is actually an application of the class equation. Well, let's see how. So let P be a group with the order of G equal to P to the n. So now the center is a subgroup. So therefore, its order has to divide p to the n. So it must be power of p. So we want to see that it at least is the first power of p. Not just one. So for this, we apply the class equation. So we look at the conjugation action. So this gives us the following. So the number of elements in the group, which is p to the n, is equal to, okay, this number. So the number of elements in the center plus sum over all x in R, where x was the system of representatives of the index of the centralizer of x in G, so x representatives. Of conjugacy classes not in the center. Okay, so we have this. So, but now let's look at this. So this is the power of p. Here, I claim that, so let me just see. So if x is an element in R, then it means that x does not lie in the center. So it doesn't commute with every element in G. So in particular, if x does not lie in the center, its centralizer is not the whole of G. So if x is in R, then x is not an element. And so index of this subgroup is bigger than 1. But you know, the centralizer of x is a subgroup, so this index must be power of p. So it's a positive power of p. So that now means that here on this side, we have p to the n, that's certainly divisible by p. And here, every summand is divisible by p. So it follows that also this one must be divisible by p. So thus, left-hand side, yeah. Yes? What? Oh, yeah, okay, that's a misprint. Thank you. Yeah, that's what I should have written. Okay, so the left-hand side is the power of p, is divisible by p. And all summands in this sum on the right-hand side are also divisible by p, so thus it follows p of g is divisible by p. And as C of g is a subgroup, it contains at least one. It's not empty, so it's at least p. Okay. Where am I? Yeah, and now we can prove this thing, that every group of order p squared is abelian. Now, quite simple. So, proposition let p be a prime, and so every group of order p squared is abelian. Okay. So let G be a group of order p squared. So we want to show that it's commutative. So that means for every element in the group, it's centralizes the whole of G. So for every x in G, we have that the centralizer of x. No, because that means every x commutes with every other G in G. So there are in principle two possibilities. Either x could be in the center or not. Obviously, once we finally prove that it's abelian, it was in the center, but we can assume that it's not. So if x is not in the center of G, then the centralizer of x contains certainly the center, but it also contains x. And x does not lie in the center. So that means we have at least p plus 1 elements. But the centralizer is a subgroup of G, so its number of elements is a divisor of the number of elements of G. So the only divisor which is bigger equal to p plus 1 of p squared is p squared. So thus C of X is equal to G. Okay, so this was this. So this was for the moment what I wanted to say about group actions. We will come back to it later. Now I want to briefly come back to the symmetric group. I want to make a somewhat more explicit description of it. In particular, I want to show that every element in the symmetric group can be written as a product of so-called cycles. So let me try to introduce this. And then we will use this to describe the conjugacy classes of the symmetric group. So the symmetric group so let me first define these cycles. So let A1 to AR be some distinct elements in the set 1n. So then the cycle, say A1, A2, and so on until AR, is just a permutation which moves everyone one step further and the last one back. So is the permutation sigma in Sn with sigma of AI is equal to AI plus 1 for I in 1 to n minus 1, R minus 1, and sigma of AR is equal to A1. Okay, this is obviously a nice permutation, and you could kind of think that you put them all in a circle and you move one step around the circle. Okay, so this is a cycle. Should maybe notice that this notation is not completely unique, because obviously this one, A1 to AR, is the same as, say, for instance, A2, A3, AR, A1. So all kind of rotations are the same element. Now I want to say that every permutation can be written in a unique way. Maybe I need some notation though. I want to need a bit more notation. So we say that, so an R cycle, so we call, R is called the length of A1 to AR, and also A1 to AR is also called an R cycle. Okay, just the words. So note that a one cycle is just the identity. So it's just the identity. because it doesn't move anything. I should maybe say, I forgot to say it here, but it's obvious from what I said. I mean, it should be obvious that all the elements which do not lie here are not moved at all. So I should have said it's a permutation which does this and send all other ones to themselves. So n sigma of n is equal to n for all, not n, I is equal to I for all I which does not lie in the set A1 to AR. That was implicitly in my mind, but obviously one has to say it. So it's just, therefore, just the identity. And the 2-cycle called a transposition. Just exchanges 2 elements. We also say that 2 cycles, so the support of the cycle so which I could write sup of A1 to AN. This is just the set of all elements contained in it, so this is just the set A1 to AN. So R I wanted. Okay, so this is just another definition. And we say 2 cycles are disjoint if the supports are disjoint. Okay, so given this, we can state our result, namely how the cycle decomposition of elements in the symmetric group theorem cycle decomposition. So I maybe just write a few facts. So the first one is, so every sigma in Sn is in a unique way up to reordering the product sigma is equal to sigma 1 times and so on times sigma, say, S of disjoint cycles such that the union of their supports is equal to the set 1n. Okay. So reordering just means that you can, obviously, we will see in a moment that they actually commute disjoint cycles, so you can put them in any order. And so the second statement is actually that they commute, so 2 disjoint cycles commute. So sigma tau is equal to tau sigma if they are disjoint. And the third one is kind kind of trivial consequence of the first. So every sigma in Sn can be written as a product of transpositions. It's a finite product. Okay, let's try to do that. So how do we want to, so the 2 and 3 are kind of trivial, so the only where we have to work a little bit is this one. And how do we want to do it? We will look at the subgroup of Sn generated by sigma, so the corresponding cyclic subgroup. This subgroup acts on the set 1 to n by, just how the symmetric group acts on the set 1 to n. And then we therefore have a decomposition of the set 1 to n into orbits. And this decomposition into orbits gives us precisely the cycle decomposition. So let's do that properly. So we take sigma in Sn. So let H the subgroup generated by sigma. Cyclic subgroup. Generated by sigma. So this is okay. Now we want to see how it acts on the set of elements from 1 to n. So then map from H times the set 1n to 1n, which sends say any element in H, which I will call tau, and I. So tau of I. No, tau is a permutation, so it's a bijection of the set 1n to itself. So is an action of H on the set 1n. So now we want to look at the orbits. So we want to choose, in some sense, representatives of all the orbits. So let 1 to BR be some elements in 1n, such that their orbits are the orbits. So such that H of B1, H of BR are the different H orbits on 1n. Okay. So it follows, for instance, that the union of these orbits is therefore the set 1n. And now what can we say? So the action is here just by it's just a cyclic subgroup generated by sigma. So we just have powers of sigma, sigma squared, and so on until. And so for each of these bi, for each I equals 1 to r, we write mi to be the smallest number such that the BI comes back to itself if we apply sigma mi times. So such that sigma k, so of BI, is equal to BI. Obviously, there must be such a one because these sigma of BI cannot all be different. I mean, the kth powers of BI for all k and z cannot be different because otherwise the set 1n would have to be infinitely many elements. And if sigma of k of BI is equal to sigma of L of BI, then we can, then it means sigma of k minus L of BI is equal to BI. And so we get this. So then we get that BI, sigma of BI, and so on until sigma to the mi minus 1 of I are all distinct. Because that's basically the same argument again. If two of them would be equal, so sigma to the L of BI is equal to sigma to the whatever k of BI, then again sigma k minus L of BI would be equal to BI, and that would contradict our choice of this k. Anyway, so this is very simple. You can check it. So, and then we have that this orbit here, h of BI, just consists, you after k steps you come back, so the orbit just consists of these elements. It's just a set. BI, sigma of BI, sigma of to the power mi minus 1 of BI. Okay, so this is just the orbit. So now we can just, and you can see how does sigma act on these elements. It just sends everyone to the next, and as sigma to the mi of BI is equal to BI, it sends the last one back. So it precisely gives us a cycle. So then, so the call this sigma I. So this thing, BI, sigma of BI, mi minus 1 I are disjoint cycles. No, because as their supports are the orbits, the orbits have to be disjoint, and these are obviously cycles. And finally, we can write our original sigma as a product of them. So now here it was called S, that's R, that's S, but it doesn't matter. So finally, sigma is equal to sigma 1 times sigma R. Namely, you can take any element x in 1n, then it will lie in precisely one of the orbits. In one of these orbits, so then X lies in precisely one of the H of Bi. So that is, we can write uniquely that X is equal to sigma k of Bi for some I in 1R and some k in 1 mi minus 1. Is it 0? Yeah, 0 mi minus 1. So if you apply sigma, so thus sigma of X is just sending it by definition equal to sigma of sigma k of Bi. So this is just sigma k plus 1 of Bi, which is just the next one in this cycle. So this is the same as sigma I of X. So on X, the sigma X the same way as the cycle sigma I. And the other elements, and for J different from I, we have sigma J of X, or now let me just see. It doesn't quite. So sigma J of X is equal to X for all them, and also not just for, okay. So it follows, so thus sigma of X is equal to sigma 1 times sigma R of X. So maybe I should be a little bit more careful. So this here, when J is different from I, then it will send every element in the orbit of X to itself. And so like this it follows. So we see therefore that sigma is equal to this. So and now this basically shows part 1. We have shown that sigma is a product of these disjoint cycles. The union of their supports is, after all, the support of the sigma I is just the in orbit of the action of sigma. So the union of the supports is the union of the orbit, which is the set 1n. And it's also clear, but I leave it to you to check, that this is unique up to reordering. Okay. Maybe I should have, okay. I think, just to be sure, so I'm a little bit dissatisfied with what this step here. Maybe I can explain a little bit better. Assume maybe I should first show what I'm going to show now, that disjoint cycles commute. So assume now we have shown that disjoint cycles commute. So then I have here So then I have this, then I could just say, if I apply these things, apply this to X, then, so for J, so this thing just is sigma I, and all the sigma X can be written like this, but how should I put it? Maybe it's not really necessary, but I mean, the main point is that every other cycle is disjoint from, one doesn't really need this. So okay, so it doesn't. So, but it doesn't really make a difference. But the main thing is that if I apply this sigma I to it, I stay in the orbit of X, which is disjoint of the supports of these, and so they act trivially on whatever I get to by this. But it might be slightly more clean to do it in such a way that I first apply sigma I and then all the others to see that, but it doesn't really matter. Okay, so let me do the, what? Yeah. No. Well, so the way I wrote it, so you see, the way I did it here, I mean, obviously, I don't know precisely, I haven't defined what the support of sigma is, but the way I have done it here, you can do it in different ways, obviously. There are actually two different ways how you could do this. In both cases, it's what's unique. Either you could say you leave out the 1 cycles, then you would not have that the union of support is 1n. But in this case, here it's better for what I want to do later to also allow 1 cycles. And then the union of the supports of the cycle is always the set 1n. Because it's just the support of a cycle is just the set of, it's just the orbit of one element there, and the union of the orbit is always the whole set that is acted upon. But you can make different definitions so that the union of the support here is something else. But I choose to do it like this. No? So if I will show an example in a moment maybe. But anyway, I wanted it to be like this, and it's also correct like this. But one could make different definitions, and then something else would be true. Okay, a bit slower than I. Okay, so anyway, the second, well, actually, there's not much to say. I just say the 2 is clear. No, because what is the point? So if you have, so one cycle will move something in one orbit, the others, the other, does not affect the part where one cycle works, so it's obviously commutative. And now the last one is also very easy. So I just take any, it's enough to say that any cycle is a product of transpositions. So if I take A1 to AR, I can write this, for instance, as follows. Just have to check. I can first set A1 to A2. Then I send A1 to A3, and so on until A1 to AR. So this product. So how does this work? So the way I write it is always as a composition of maps. So A1 is sent to A2, and A2, so A1 is sent to A2. Now, and A2 is sent to A1. Now this new A1 is sent to A3. And so it means that altogether A2 is sent to A3. And if you look what is happening here, it gives you precisely this. And so you can see we have written this arbitrary cycle as a product of transpositions. and this was just a cycle, and then every element in the symmetric group is a product of cycles, so it's also a product of transpositions. Okay, this was this. Now we want to use this to describe the conjugacy classes. This was the reason why I had insisted on it like this. And maybe I should give I can give an example. I don't know, well, I can just. So we want to describe the conjugacy classes of the symmetric group. And we will see that they are parameterized by the partitions of n. So let me remind you what a partition is. So a partition, a positive number, so non-negative number, is a tuple so at least that's how I want it. So of numbers n1, n2 until nr of integers, of positive integers, with so which are decreasing. N1 is bigger equal to N2, is bigger equal to N3, and so on. And the last one should still be strictly positive. So, a bit here, yeah. And obviously, it's supposed to be a partition of n, so the sum of all these numbers should be n. Whatever the partitions of 3 are, whatever, 3, 1, 1, 1, 1. Okay? So, definition. That sigma be an element in Sn, can write sigma equal to sigma 1 times sigma r. It's cycle decomposition. So by reordering the cycles, we can assume that their length is decreasing. So by reordering, we can assume that, yeah, maybe didn't introduce the notation, but so this is, I write L of sigma 1, so this is the length, bigger equal to the length of sigma 2, and so on. It's bigger equal to the length of sigma r. So then, and obviously, the length of all the cycles are positive numbers, and we know that the length is just the number of elements that are in the cycle, so the sum of their supports the whole of n, so the sum of these numbers is n. So then L of sigma 1, L of sigma r is a partition of n. And this is called the cycle type of sigma. Okay. For instance, I mean, just to have an example, it also maybe answers the question before. So if sigma is whatever, let me see, 1, 2, 3, 4, 5, 6 in our old notation, 2, 4, 5, 1, 3, 6. So what does it do? So I can try to write this as a product of cycles. So 1 goes to 2, 2 goes to 4, and 4 goes to 1. So, so now the next I'm missing is 3 goes to 5, and 5 goes to 3. And 6 is sent to itself. So this is the cycle decomposition. And the cycle type is 3, is the partition 3, 2, 1 of 6. So that's an example. So now we want to understand the conjugacy classes of the symmetric group, and we want to see that they are in bijection with the partitions of n, via the cycle type. So as we are talking about conjugacy classes, maybe good to first see what happens when we conjugate a cycle. This is just the following remark. So let me take any permutation, anyway kind of useful for some computations, tau in Sn, and take a cycle, A1 to AR cycle. Then when I conjugate this cycle by tau, I get again an R cycle, and it's just the R cycle given by the images of these elements under tau. So then tau A1 to AR tau to the minus 1 is just tau A1 tau. Okay, so this is basically, this is obviously trivial if it's true at all. So I take tau A1 to AR tau to the minus 1. I apply it to tau AI. Well, this cancels out, so this is just tau A1 to AR of AI. And this cycle sends the AI to the next one with the convention that the next one from R is the first. So this is just tau of AI plus 1. And so we see precisely that what this thing does is sends precisely AI, tau of AI to tau of AI plus 1. And obviously everything which is not among the set is not moved at all. And so we get this fact. And then we can use this to see proposition. So two permutations. Sigma tau in Sn are conjugated if and only if they have the same cycle type. So this is, the second is consequence. So the number of conjugacy classes of Sn is equal to the number of partitions of n. Okay, so now this is basically, the first one is basically this statement here. So if sigma equal to, say, sigma 1 times sigma r is a cycle decomposition, and tau is an element in Sn, then if we take tau sigma tau to the minus 1, this I can also write as tau sigma 1 tau to the minus 1 times and so on, tau sigma r tau to the minus 1. I just put tau and tau to the minus 1 in between, always alternatively. And so by what we have seen here, if this is a k-cycle, then the corresponding thing is also k-cycle. So we also get this is the cycle decomposition into cycles of the same length. So this is cycle decomposition of tau sigma 1 cycles of same length except and so it follows that if they are conjugated, then they have the same cycle type. So conversely, it's more or less the same. So thus sigma and tau sigma tau to the minus 1 have the same cycle type. Conversely, we can basically retrace our steps. So where am I? I don't even know where I have my page. Okay. So conversely, if say what do I want, sigma and pi have the same cycle type, basically it's also obvious we can write sigma equal to sigma 1 times sigma r, pi equal to pi 1 times pr, where the corresponding things have the same length. So with I equal to, say, A1I until A, say mi, I, for some number mi, and pi in mi, I, no, because the cycles have the same length, it's the same number, the same, there we have cycles of the same length, so this is just for some elements, ai, bi, and then we define a bijection. Tau from one end itself, so tau, which is an element in the symmetric group, which just sends h bij, aij to the corresponding bij. So by tau of aij is equal to bij for all I, what is it, from 1 to R and all j from 1 to mi. And as the union of these, of the supports of the cycles here is the whole of the set 1n, this defines a bijection of 1n to itself, so an element of the symmetric group, and by definition, by the remark, we have that if we take tau sigma tau to the -1, this will be equal to pi. Because we have just, the thing was just that. Okay. So what was else was there to show? The last thing, so in principle we have now shown this, but in principle you still might want to, to be completely sure, you have to see, so here we have just see that two permutations are conjugated if and only if they have the same cycle type. In theory, there could be more cycle types that then come from permutations, but obviously this is not the case. And so we just have to see that every cycle type, so that every permutation, every partition can occur as a cycle type, and that's certainly true. So we have seen that the cycle type defines an injective map from the conjugacy classes of n, the partitions of n, and so we only have to see its surjective. So surjective. So we have to find, so let's take any partition, so let N1 and R be partition. Of n, then we can just write something which has that as a cycle type. We just write down some cycles of this length. It's trivial. So we take, for instance, 1 until n1 this cycle, then n1 plus 1 until n1 plus n2, and so on. The last one is the sum of all of them minus the last, plus 1 until n. Has this cycle type. Okay. Yeah. Let's see. Okay, I was a bit, so my time seems already to be up. I'm a bit surprised. But anyway, so I did a little bit less than I expected. So next time we will finish this about the symmetric group by talking about the sign of a permutation and show its properties and introduce the alternating group. And then I will start discussing the Silo theorems. Okay, thank you. Are there questions? No, it's okay. No questions. Well, somehow it's time passed a little bit faster than. Okay, thanks.